Hi, I'm Larry Waldrop. I'm the administrator of SonoWorld, and here at this special report from RSNA 2012, my guest is Mike Cannon. Mike, thanks for joining me today. Mike's been involved in the development of multiple specialty ultrasound systems over his career, and more recently he's been central to the development of a landmark achievement in ultrasound technology. Here at RSNA, Siemens will be presenting the world's first ultrasound system using wireless transducer technology. And what that means is that there's no cable between the transducer and the ultrasound machine. Mike, that's been at the top of everybody's wish list for decades, and it's an amazing, amazing accomplishment. Could you tell us a little bit about the system and how it works?
Sure, I'll do that. Thank you very much. I appreciate the opportunity to talk, and I certainly appreciate all the great work that SonoWorld does. Our team of engineers started several years ago with the concept of developing an entire system that really improved the use of ultrasound in interventional procedures. The whole goal was really not so much just to develop a wireless transducer, but to develop a system that worked better in the sterile field. And our goals there were to try to improve the workflow of the clinician or the physician doing guided procedures when they had to control for risks of infection and setting up the system and optimizing the system. And when we looked at the overall problems that we had, we then concluded that what would really make a big difference was the wireless transducer. So we didn't start out just saying, let's build a wireless transducer. We said, let's solve a clinical problem, and the wireless transducer became a big part of the solution there. A lot of people, as you mentioned, a lot of clinicians, a lot of ultrasonographers have been dreaming about wireless transducers for a long time. And the reason we haven't seen one until now is that the technical challenges are massive and daunting.
I can imagine.
And we embarked on it also from a point of view of, let's look at what newer technologies are available that might solve these problems that weren't available earlier when people had that desire, had that longing for a wireless probe. And a number of things happened over the last few years that facilitated this capability. And those came from a number of different technology areas. Some radio technologies that became adopted onto international markets, some imaging technologies that we pushed further that had been used in a piecemeal fashion in ultrasound, we pushed farther. And then also we took advantage of the miniaturization of electronics that we've seen in so many fields, and we've seen it in ultrasound, but we pushed that farther because in this system, a lot of the ultrasound image formation is taking place in the transducer, much more so than in other systems, whether at the lower end or at the premium end of the market.
Interesting. I would have never dreamed that it was almost incidental that you had to develop the wireless technology to solve the clinical problem. That's pretty neat. You're moving, obviously, a massive amount of data between a transducer and the system incredibly fast. Does this create a problem with interference with other systems, particularly in an area like interventional or intensive care?
There are two problems there. One is the amount of data you need to move. The first job we had was reducing that data drastically while maintaining good image quality. That was the first technical challenge. Then the next challenge is getting a radio that will carry even the rate that we got it down to. Getting a radio that would transport that reliably was a big challenge. And then a subset of that is making sure that radio is benign in the interventional setting or in the patient care setting, and also is immune to other RF energy that's taking place there. So there were definitely manifold challenges there. A key part of the first step, reducing the data, was to do a certain amount of image formation in the transducer. So the transmit and receiving, the digitization of the image data at a very early stage, really at a raw stage, and some filtering and formatting of the data takes place in the probe. That's one of the first steps that we use to get that data rate down. We're using also, a key part of it was we're using the synthetic aperture technique to a really large extent. And so a lot of the image quality, a lot of the image resolution is really formed synthetically, retrospectively after we've transmitted it on the back end of the system. And so all of our focusing is done computationally. In a conventional system, you're used to the acoustic transmit is formed. You have transmit focusing that takes place, and you have focal zones that the user sets, and that is a key part of your resolution. In our case, we're doing all of that really on the back end. And that was a big step in reducing the data, reducing the power in the probe. It gives you many benefits also. It really has some nice advantages in image quality, and it also gives you a uniform focusing throughout the field of view without the user needing to interact to say, where do I want to set my focal zones?
Wow, that's a major change without needing to set focal zones in advance. There are obvious advantages both ergonomically and in terms of just the convenience of not having a cable between the transducer and the ultrasound instrument. Are there other benefits of this? How is it going to change the ultrasound field?
Well, there are several steps. Our first target, the initial thrust as far as application and use, will be the sterile setting and interventional procedures. That's really just the beginning. This is at an early stage as far as the technology goes. It's at an early stage in terms of the product implementations that we'll see as a part of Siemens ultrasound. Within that first targeted usage, the advantages of wireless are several. One is it improves the setup. It has workflow improvements because it's faster to prepare the probe to put it in a sterile cover. You don't have to worry about dressing the cable. You don't have to worry about, once you're set up, once you start scanning, has the cable maybe gone out of the sterile field and is it back in? Is the cable coming over the patient? Those are the key initial advantages that we have. We're also seeing, as we've done evaluations of it, that in a number of interventional environments, it gives you more flexibility in terms of where you set the system and where the person is positioned that's doing the imaging. With a cabled system, it's harder to do that because the cable obviously has limitations in the distance you can create between the probe and the system. In our case, we actually have a little bit more latitude there. Longer term, as the technology expands and as we look at it in other applications, there will probably be many other advantages. We know with the ergonomic elements in just even routine scanning that it might help with, and we will be exploring those.
Well, that's very exciting. I see you have one of the transducers here. Obviously, we're curious as to what that looks like and how it works.
Okay, we are introducing 3 transducers initially, 2 linears and 1 curvilinear. As you see, the probe is formed and shaped not too differently than a conventional probe, but it has a lot going on inside of it, so its shape and form factor are a little bit different. This, as I mentioned, it has an entire ultrasound front end in it. It's doing a lot of digital image processing. It's got a custom high data rate radio that transmits the ultrasound energy. And of course, it has a battery, a removable battery, that allows the user to scan for a really pretty long period of time and then can easily change it if they need to replenish the battery. So the overall form factor, though, still works very well in terms of being handheld and having a good feel in the hand. And we find, as we've had people testing it and we've used it, that being able to operate without the cable pulling on you produces all sorts of really nice advantages in scanning. A couple other nice things about the probe that are worth pointing out is that it has controls on the probe where you can control all of the real-time parameters from the probe. Right. And when we designed the whole system and the user interface, we kept all of that in mind because many times these users are set up, they're in the sterile field, they can't touch the system, and they need to sometimes make a change. Sometimes you just have to change gain, or you have to change depth, or you've got the wrong preset. And with this, everything you can do from the system as far as real-time controls, you can do from the probe. And the controls we have on the system are mirrored here, so you can turn color on and off, you can change gain, you can change depth, you can save, and that is a major advantage, and it really helps. Once you're set up, it helps the other personnel in the room do the things they need to do. They don't need to come over and babysit the system because the person scanning needs some help.
You mentioned that you're going to be launching the system with 3 transducers. Can you tell us about which 3 you're going to be having?
Sure. We have three arrays that we think cover a wide spectrum of the applications that we would go after and users would want to employ the system for. This one we call the L135. It's a mid-frequency linear, so kind of a workhorse, vascular access, small parts, musculoskeletal applications. We have another high-frequency linear. We call this a 13.5, so it is especially good for more shallow imaging, small parts, nerve imaging, smaller patients. And then we have a curved array. We call this a C52. Obviously, abdominal applications. It can be used in other non-abdominal applications where you need a deeper field of view.
Mike, the transducers are much smaller than I would have expected them to be, given what they have to do. How far away can the ultrasound machine be from where the transducers are and still have the two function together?
The technique that we use is a radio technology called ultra-wideband. It's a technology that's really suitable to high data rates. It's a very low power radio, which has a lot of advantages in the medical setting. And it is a very robust one in terms of link quality in the kind of environment or the kind of distances that we're talking about. It's designed and specified that a user can operate typically within about 3 meters. We say try to stay within 3 meters. You can actually, if you're set up right, you can go farther than that, but most of the applications don't need to be more than that. You do have to maintain some awareness of the relationship between the probe and the system as far as that distance, and you can't get too far out of a line of sight, but in the evaluations that we've done, the link is very robust, certainly up to those distances.
Wow, that's quite a long distance. What happens if I forget and put one of those transducers in my pocket and walk out with it?
The issue of the untethered probe disappearing has certainly been raised, and it's definitely a concern. It comes up whenever we go out and visit hospitals. We have built some tools in for trying to manage that. We have, in addition to the dedicated radio that manages the ultrasound data, we have a separate radio that tracks the relationship of the probe to the system, and if they get too far apart, the probe will be alerting you with sounds, and there will be a message on the system, and so there are safeguards that have been built in to try to minimize that problem.
Cool. So I can't walk out with one in my pocket today.
We'll try to prevent that.
Okay. Mike, the transducers are pretty remarkable in the simplicity of their design, and it looks like the console carries that design through. Can you tell us a little bit about the console and how it appears and what kind of information it's going to be displaying?
Our goal was certainly to communicate simplicity and design a system that to the user interface appeared very simple. And the console, as you can see here, was designed to be very compact but still have a really high quality, really good large display that uses LED technology, so it has excellent brightness and excellent resolution, really good color flow quality. The overall package, as you can see, it's very small footprint, designed to be really mobile, flexible as far as where you set it up and how you move it around. And the user interface is designed so that, as I mentioned, it can be controlled from the probe, can be controlled also from the system, but in a way that's very easy to use. And the controls that you need to adjust in this type of application are up front, very easy to find, and we use an extensive system of exam types and presets so that hopefully most of what you do, you don't really need to make system changes at all. So let me give you a little overview of the system. The control panel, as you see, is very simple. It relies primarily on these two knobs that control your real-time settings. This outer knob highlights one of the controls, and then the inner knob will activate it. And that function is replicated on the probe, where this highlights a feature, and then one of the buttons activates that particular feature. The use of that I'll demonstrate here. So if I am set up, I'm ready to start scanning, and the system is frozen, I can do that from the probe. I unfreeze it, then I get my real-time controls. I can save. The system does digital saves. It's DICOM compliant. You can export in a DICOM format or in multimedia formats. And then we have large buttons for your basic controls up front, so things that you need to do even in this type of exam, change gain, change depth, turn color on and off, can be done from the probe as well as from the system if you have access to this system. I mentioned you have exam types, so hopefully you can select, say you want to do small parts, you want to do a thyroid exam. We set things up so that hopefully we hit really what you want setting-wise, and you don't necessarily need to change much at all. And that also, as you see, can be selected from here. At the same time that we want to keep things fast and simple, we want to give users a lot of control too. So there is another level, more sophisticated users, power users, or for particular patient presentations, you can go deeper so that if I'm in B mode and I want to change my compounding approaches, my speckle filter, or I want to adjust dynamic range or fine tune the image, I can do that. But it's at a level where if I don't want to delve into that or I don't feel that I need to, it's buried. It's not distracting you, and for newer users or really busy users, it doesn't get in the way. Another important part of the design is that we have a large high-resolution display with LED technology, which gives you a very bright image, which is critical for this use because unlike a lot of conventional ultrasound, the scanning is typically done in a room with very bright lights on. And so we designed the image quality and the processing and the presentation to take into account that this is often done in a room where you do not have the ability to lower the lights.
Mike, this is an amazing piece of technology. When can I get my hands on one?
Well, thanks again, Larry, and thanks to Sono World. The product does have its FDA 510K clearance. Siemens will be showing it and launching it at this RSNA, and we look forward to meeting you and others in the exhibit there.
We'll be there. We'll be there. Thank you, Mike.